So what we're going to be doing today, we're going to start talking about like frequency responses. And as an application for the frequency responses, we're going to talk about like filtering, right? So far, all we dealt with was we have a circuit, there is some input to it, what is the output, right? That's all we did. I had like my sources. It was either like a constant source or like a sine wave. We had like some output, which is voltage across something or current through something. Given that input, we could always like find the output, right? But let's think about it through like another perspective. Let's think about the whole circuit as a system, right? And this system has some input and has some output, right? So for example, let's just say I have this circuit, very simple circuit. It's an RC circuit that we talked about. We have some input voltage V in, we have some resistor R, and we have a capacitor C. And let's just say voltage across this capacitor as my output, right? Instead of looking at the circuit as this circuit, we can think about it as a system. So we can think about it as a system. With input V input and the output V out, right? And this relationship between the input and output is described by this system, right? The question is, can I find any representation for this system? Or in other words, as soon as I change my input, given this system, can we find the output? The answer is no. In general, we cannot do this. Under very special circumstances, when the system is linear and time invariant, we can actually find a very nice relationship between input and output, right? Good news is, whatever we're dealing with in this class is indeed linear and time invariant. So as soon as we establish some relationship, we can use that formula and go ahead and find the output whenever we change it, right? So it turns out if system is linear and time invariant, for short, we call them like LTI system, then we can find the output using this formula. The input as a function of time convolved with the system, let's call our system h of t. So convolved with h of t, right? Which we define the convolution to be this integral from minus infinity to infinity, b input tau, h t minus tau, d tau. And we know convolution is commutative, which means convolution of Vn and Ht is the same as convolution of Ht and Vn, and therefore we can write this as integral from minus infinity to infinity of h of tau, Vn t minus tau, d tau. Right? There are a few words in here that I haven't defined really, like linear and time invariant. If you're an electrical engineer, you're going to take like 2 or 3 in signal systems. They're going to define like these things in details. But to give you like a very quick idea of when a system is linear, what it means is that it is additive and homogeneous. When we're talking about like time invariant systems, what it means is that if I change my input by some t naught, the output would change with the exact same value of t naught, right? But again, we're not really concerned with these two terms. All the circuits that we're dealing with, they're linear time invariant. So if I want to find the output, I can always convolve the input by this system, h of t, right? We call this h of t impulse response. Again, we're not really concerned with it. I'm gonna let you know what it is in case you saw it somewhere. So this H of t is called impulse response. Right? So as soon as I have like the impulse response of the system, as soon as I have input, I can find the out. Right? I have to compute this integral. But looking at integral, it is quite scary. Why? Because look at like the first definition of it. What I need to do is that I have to look at H of t. I have to look at the inverse of it, then shift it by this t, and then sweep it over the input and find the area underneath. And I have to do it for all possible shifts that I have. So it's quite scary. It's quite difficult to do. But what we learned so far is that there is a possibility, there is always a possibility to go from time domain to the frequency domain. It turns out if I go from time domain to the frequency domain, this scary convolution becomes multiplication, which is much, much easier to compute. So going from time domain to frequency domain, it turns out I can compute the out as a function of frequency equals my input as a function of frequency times h of omega. Right? So this convolution became multiplication. We just needed to look at input h and v out, all in frequency domain. We call this h frequency response. This h is called frequency response. Again, in 203, you're going to learn this frequency response as nothing but the Fourier transform of this impulse response. As a matter of fact, with whatever we have over here, if we go from time domain to the frequency domain, it's just a Fourier transform or Fourier series. Right? But so far, we know nothing. We just know if you go from time domain to the frequency domain, this would be the relationship. Right? So in general, we can define the ratio of output to input as our impulse response or frequency response. Right? Again, that does not really have to be like voltage. It could be anything. As long as I have my output, I have my input, I can divide them. I get like a function that is my frequency. So let me quickly rewrite this, and then we're going to make that. So we can rewrite V out as a function of frequency equals V in omega times h of omega, and get h of omega equal V out of omega divided by V in. In general, any ratio of output to input is called frequency response. Obviously, when I'm talking about the ratio of output to input, I mean the ratio in frequency domain, right? I do not mean in time domain. So this is in frequency. Right? In general, we have like 4 different ways of looking at it, right? So this h of omega can either be V out over V in of omega, or it can be I out of omega divided by I in of omega, or it can be V out of omega divided by I in of omega, or that can be I out of omega divided by I in. Right? These are all the possibilities that we have. Right? There is always like some input voltage or current, some output voltage. Okay. Right? So these are all the things that. Like any function that we have, we want to know like what this h of omega actually looks like. We got to be able to plot it, right? We want to know like, okay, if it's going up, it's going down, like what does it look like? Can we plot this h of omega? Can we? The answer is no. We cannot plot it. Remember, as soon as we go from time domain to the frequency domain, we're dealing with complex numbers, right? So this h of omega, note that this h of omega is basically a function from complex numbers to complex numbers, right? And we said complex numbers are very, very similar to R2, right? So this function is going from R2 to R2, right? If I have a function that goes from R2 to R2, where can I plot it? I can plot it in R4. Remember, if you have a function y equals f of x, what are you plotting? You're plotting the tuple x and f of x. So it happens in R2, right? Over here, I have two inputs and two outputs. So it happens in R4. So I'm not able to plot it, right? And therefore, we cannot plot h. Well, we're still interested in knowing like what it looks like. Where does this h of omega go? It goes to complex numbers. So instead of plotting h of omega, I can plot magnitude of it or the phase of it. So instead of like going to R2, I'm going to R. Right? So instead I can plot that. We plot magnitude of h of omega. And phase of it. Now these are possible to plot. Yes. Oh, this is the correct thing. So this is going to be, which one is missing? So it could be, that should be the end. Thank you. Right? So we got to be able to like plot it. It turns out even plotting this could be very difficult. So we're going to have like some approximation for the plot. And we call it a boat plot. We're going to talk about it next week. So the approximation here is called boat plot. Just an approximation. But it's good enough. It tells us like where we're going down, when we're going up, it tells us everything. But it's just an approximation. It's just a linear approximation of the actual function magnitude and the phase. Right? We're going to talk about it next week. But let's look at this h of omega and try to understand it a little better. So let's just say again, I have my system over here with input x of t, the system h of t. Let's just assume it's LTI. I get some output y of t. I know the relationship between input and output is through this convolution, which we said, since we can uniquely go to the frequency domain, I can write this as y of omega equals x of omega times h of omega. Basically, the convolution becomes multiplication, right? And given this, I can compute h of omega, which is my output, y of omega divided by x. Right? Which again, we said this is a complex number. Right? If it's a complex number, what is the magnitude of this? Since h of omega is a complex function, what is magnitude of h of omega? Remember, h of omega is that division. What is the magnitude? It's the magnitude of the numerator divided by the magnitude of denominator. So it's magnitude of y omega over x of omega, which we know it is magnitude of y omega divided by magnitude of x. What is the phase of h omega? What is the phase of a division? We know it. What is it? I have to subtract phases, right? So if I divide two complex numbers, I divide the magnitudes, I subtract the phases. So it's the phase of y omega minus the phase of x. Right? Now we know this. Let's talk about like its very first application, which is a filter. And filters are basically circuits. Application. Filters are in general circuits that can keep or eliminate a range of frequency bands. We daily use filters. Can you give me an example of it? The very simple example is your ear. Your ear is a great filter. It basically removes all high noises. And that's why you're not deaf. So it's a very great filter. Your phone is also a great filter. So when it receives all like basically like messages and everything, it removes all the noise from it. So you can actually hear me talk on the phone. Otherwise, you're not going to be able to hear me. Right? Those are actually complex filters, but they're filters nonetheless. Right? But the whole idea behind filters is that it's a circuit that keeps or rejects some range of frequency. Okay, so let's define. Filters. They are circuits that keep or eliminate a range of frequencies. Right? In this class, we only learned about resistors, capacitors, and inductors. And these are passive elements. Given these passive elements, we're only able to build 4 types of filters. Low pass filter, high pass filter, band pass filter, and band stop. These are the only filters that we can build with passive elements. So given passive elements are C and L, we can only build 4 types of filters. Type 1, it's a low pass filter. As the name suggests, it lets all low frequencies pass and rejects higher frequencies. Right? So it keeps low frequencies and rejects high frequencies. If I want to draw it pictorially, if I look at the magnitude of h of omega versus omega, what I want to do is that I want to keep low frequencies and reject high frequencies. So it should look like this for some frequency omegas. And the value over here is 1. In a second, I'm going to explain why it should be 1. But that's what it looks like. What it says is that it's going to keep all the frequencies less than omega c and rejects all the frequencies that are greater than this omega c. Right? We call this omega c cutoff frequency. Right? So this is a cutoff frequency. Right? Type 2. We have high pass filter. Again, as the name suggests, it rejects all low frequencies and keeps high frequencies. Right? So it keeps high frequencies and rejects low frequencies. If I want to draw it, I'm going to draw the magnitude of it. The magnitude is for all frequencies less than this omega c. We should reject and keep all the frequencies that are greater than this omega c. The value here is 1. Right? Is that clear? Definitions are clear. Type 3 is called bandpass filter. And what it does is that it keeps some particular range of frequency and rejects whatever that's outside that range. Right? So it keeps some particular range of frequency and discard outside this range. Again, if I want to draw it, what it looks like is, let's just say the range I want to keep is between omega c1 and omega c2. So it keeps that and rejects the rest. Right? And the last type is the band stop filter. Which rejects a range of frequency and keeps the rest of them. Right? It's basically the reverse of this. So it stops a range of frequencies and passes the rest. And if I want to look at it, let's just say I want to look at the range between omega C1 and omega C2. So it basically keeps whatever less than omega C1 and whatever greater than omega C2. Notice over here, I only drew the magnitudes. I didn't draw the phase. In a lot of applications that we're dealing with, the magnitude is the one that's important. And a lot of applications are not sensitive to the phase. For example, your ear is not sensitive to the phase, and it's only sensitive to the magnitude. Having that said, there are a lot of applications that are sensitive to the phase. So we got to learn how to plot both magnitude and the phase. But for this application at the moment, we only need to look at the magnitude, and that's why I drew the magnitudes. Right? We're going to talk about the phase as well, but magnitude is the one that's. What's important here is that if I look at like these four types, these are the only filters I can build with R, L, and C. Right? And since both type 1 and type 2, I only need to have one cutoff frequency. It turns out if I want to build these two types of filters, I can build it using like a first order circuit. And since for the type 3 and type 4, I need to have two cutoff frequencies, I cannot do it with the first order, but I can do it with the second orders. Right? That's why type 3 and type 4 filters are known as a second order filters, and type 1 and type 2 filters, which is the high pass and low pass, they're known as the first order filters. Okay? Any question on this before I give you like some intuition about why they're actually called filters? Yes. No, the design would be a little like different. That's called like, you can just design it using like Butterworth filter and things like that, or Chebyshev filters and things like that. The design would be a little different than this. But these are the only ones you can do with RLC. Right? Any question on these? So let me give you like an intuition to see like why they're called low pass filter, high pass filter, band pass filter, band stop filter. So intuition. Let's assume we have a low pass filter. So assume we have a low pass filter. What it means is that my system is a low pass filter, right? So I have my X of t. It goes to my system, which I know it's a low pass filter. It provides some Y of t, right? Again, it's quite hard to analyze it in time domain, so we're going to take it to the frequency domain. So I'm going to have this X of omega fed to my low pass filter, which I know the magnitude of this low pass filter looks like this. Right? And I get some output Y of omega. Right? What is this output? This output is X of omega times H of omega. Right? So let's assume my input X looks like this. This is absolute value of X of omega. Right? And obviously this is my H of omega. Right? What is this y of omega? If this black curve over here is my x of omega. Again, I have to multiply this x of omega by this h of omega. How do I multiply two functions? Multiplication is pointwise. So I got to do it each point by each point. So up to this point, omega c, I am multiplying everything by this magnitude. But we said the magnitude is 1. So what does that tell me? It tells me up to this point, omega c, I spit out exact same as my input. How about for all the frequencies greater than omega c? I'm multiplying 0 by that. So if I look at my output, again, I'm looking at the magnitude of it. So up to this omega c, I have exactly the same as my input. The output after omega c would be 0. So this is y of omega. That's exactly x of omega. Right? So imagine if this one was 2, for example. My output wouldn't have been exactly the same as my input. The filter, what I want the filter to do for me is to just like pick out that range of frequency for me. And if this one was 2, it wouldn't have picked out like the same function for that range of the frequency. It would have amplified the magnitude of that function. So that should be 1 then. Right? So if I write this over here, my output is x of omega for all frequencies less than omega c. Or for frequencies greater than omega c, the output is 0. Right? I can say the same thing for the high pass filter. I can say the same thing for the band pass filter and band stop filter. Right? But now we're at it. Let's look at the circuit that can give us a function that looks like this. First of all, this is the ideal low pass filter. In real world, there is no way we can get such sharp edge. It's just not possible. The way that we can get it, this edge is being smoothed out. So instead of having this sharp edge, it actually goes down a little. Right? But let's just see if we can build a circuit that can give us something remotely similar to this. So let's look at this circuit. So let's look at some input voltage here, some resistance, and some capacitance. And look at voltage across the capacitor as my output. What I'm claiming is that if I look at the ratio of output to input, it is something similar to this curve that I have for a low pass filter. Well, let's take a look at it. First of all, this is a first order circuit. I only have one storage element, right? How do I analyze it? We're going to go to the frequency domain. We just learned it, right? So let's go to frequency domain. Go to frequency domain. So this is a function of time. This is also a function, right? If I go to frequency domain, the topology of my circuit would not change. So I have Vn as a function of omega. Resistor would not change. Capacitor becomes 1 over I omegas, right? And what I'm interested in is this V out as a function of, right? Do here I can find V out very quickly. Yes or no? Yeah, it's a voltage divider. So V out as a function of omega is 1 over I omega c divided by R plus 1 over I omega c times V input as a function of omega. Right? What is the ratio of output to input? Well, I just need to like bring this V input down here. Right? So V output omega divided by V input omega is 1 over I omega c divided by R plus 1 over I omega c. Right? And this is my frequency response. Right? Yes.
Can you, I think from our earlier classes, you could write 1 over I equals C as negative I over C.
Yes. Let's simplify this a little. Let's simplify this. I'm gonna keep the numerator as it is. I'm gonna find a common denominator over here. So I have R times I omega c plus 1 divided by I omega c. Right? This I omega c and this I omega c cancel each other out. So what I end up getting is 1 over 1 plus I omega RC. Right? But if I look at H of omega, it is 1 over 1 plus I omega RC. To compare this to this function, what do I need to compute? I need to compute the magnitude of this. Right? I know the magnitude of this H of omega is 1 for all the frequencies less than omega c. And it is 0 for all the frequencies greater than omega c. Right? What is the magnitude? What is the magnitude of H of omega? It's the magnitude of the top divided by magnitude of the bottom. What I have down here is a complex number. What is the magnitude of this complex number? Square root of real part squared plus the imaginary part squared. Right? So it is 1 over square root of 1 plus omega squared R squared. Right? If you plot this, what it looks like is something like this. How do I know it? Well, let's look at this magnitude when omega is very small. So if omega is around 0, what is magnitude of H of omega? I just need to like plug 0 here, right? So it's around 1. So for very low frequencies, this approaches 1. So over here, I have a 1, right? What happens if omega approaches infinity? Again, if omega is pretty big, this term dominates this 1. So what I have down here is 1 over omega. So for very high frequency, it decays like 1 over omega. And if you go to infinity, that 1 over omega asymptotically is 0. Yes. Because this is the imaginary part. I is not part of the imaginary part. Right? So if it goes to infinity, absolute value of h of omega is very similar to 1 over omega. And if omega is indeed infinity, that approaches zero, which is exactly like the graph that I have over here. If I compare this to my ideal low-pass filter, this is my ideal low-pass filter. This is ideal low-pass filter, which I know I have this omega c. So for this graph, for this flat graph that I have over here, I got to be able to determine what this omega c is. It turns out this omega c is where the magnitude of this h of omega is 1 over square root of 2, which is basically negative 3 dB. Right? We're going to talk about dB like later. But for now, to determine like what this omega c is, this omega c is the frequency that the magnitude of h of omega is 1 over square root of 2. Right? So if I ask you to compute, come on. Back to live. Thank you. So if I ask you to find this omega c, you know this magnitude, right? You're going to put this equal to 1 over square root of 2. You have r and c, and you can find that omega. And that corresponding omega is this omega c. Right? So you have this magnitude. You put this equal to 1 over square root of 2. You can compute omega. You can solve for omega. And that gives you that omega c. Again, that 1 over radical 2 is not some arbitrary number. It's basically when you drop by 3 dB, which is 20 times log 10 of this absolute value. We're going to talk about it later. Just so you know, it's not some arbitrary number. Right? So if I build like this circuit, this RC circuit, and look at voltage across the capacitor, that indeed gives me a low-pass filter. Right? How about a high-pass filter? How about a high-pass filter? So this was the intuition for low-pass filter. We can do the same thing for the high-pass filter. All right? For a high-pass filter, intuition high-pass filter. Again, the whole idea here is that I want to keep high frequencies and reject low frequencies. So if I have my input x of omega, I want to feed it to something like this. And I want to get this y of omega, which I know this y of omega must be the exact same as x of omega when omega is greater than omega c. And it's 0 if omega is less than omega c. Right? Which if you actually compute like this h, it's y omega divided by x of omega, right? So it's 1 for all omegas greater than omega c, and it's 0 for less than. Right? Let's see if we can actually build a circuit that does this for us. Right? Let's this time look at this. Again, a first order circuit with a capacitor and a resistance R. This time, instead of measuring voltage across the capacitor, let's compute voltage across the supply. Right? We just learned we can compute this in the frequency domain. So I have Vn of omega. I can replace the capacitor by 1 over I omega c. The value of resistance would not change. I can find the out of one. Right? What is V out of omega? It is R divided by R plus 1 over I omega c times Vn. Right? If I look at H of omega, which is V out of omega divided by Vn of omega, that is R over R plus 1 over I omega. All right. Let's simplify this a little. I have R divided by I omega c times R plus 1 divided by I omega c. I have to take this to the top, so I get I omega RC divided by 1 plus I omega RC. Right? So H of omega, in this case, is I times omega RC divided by 1 plus I omega RC. Right? Let's look at a magnitude of that to see if it actually resembles the ideal high pass filter double. What is the magnitude here? Well, it's the magnitude of the numerator divided by the magnitude of the denominator. Right? So it is omega RC divided by square root of 1 plus omega squared R squared C squared. Right? If I plot this, it actually looks like this. And this is 1. Whereas the ideal high pass filter looks like this. How do I know this looks like this curve? Let's look at the low frequencies. So to check for high pass filter, let's look at absolute value of H of omega when omega is 0. What is it when omega is 0? It's 0. I just need to plug 0 in here. The numerator is 0, therefore the whole thing is 0. Right? So it is 0, which is what I have over here. What is the magnitude of H of omega when omega approaches infinity? Remember, this omega squared R squared C squared dominates this term, this 1, right? So the denominator is pretty much omega RC. So I have omega RC and omega RC. So it approaches 1. Okay. So this is basically omega RC divided by omega RC, which is right. Again, to find this omega C, we're gonna have to find the frequency that absolute value of h of omega is 1 over square root of 2. By the way, this is not the only way to build like a high pass filter and a low pass filter. But whatever way we build it, we can build it with like inductors. It's gonna be a first order circuit. Okay? We can build it like in a very complicated manner, but it's still as a first order circuit. Right? We can do the same thing for the band pass filter. So let's talk about band pass filter. So intuition, band pass filter. Remember what a band pass filter was. It keeps a range of the frequency and rejects whatever that's outside that range. So if I have my system with an ideal frequency response, which I know it should be something like this. This is 1, this is omega C1, and this is omega C2. I get my y of omega, which I know this y of omega is exactly x of omega for all frequencies between omega C1 and omega C2, and 0 otherwise. Right? We know since we have like 2 cutoff frequencies, we cannot build this with only 1 storage element. So it must be a second order filter. Right? So let's just say I have this circuit. I have some input. I have an inductor with value L. I have a capacitor with value C. And I have my resistance over here, R. And I have voltage across R as my output. Right? To analyze this, I have to take it to the frequency domain. If I take this to the frequency domain, again, the topology would not change. This inductor becomes I omega L. This capacitor becomes 1 over I omega C. This resistance does not change. And I can compute V out of omega. How do I compute this V out of omega? What is this V out of omega? It's a voltage divider, right? So this V out of omega is R divided by I omega L plus 1 over I omega C plus R times V in. If I compute H of omega, it's V out of omega divided by V in of omega. It is R divided by I omega L plus 1 over I omega C plus R. Right? To save us some time and not write I omega all the time, let's just define I omega as S. Right? So define S to be I. Right? Later, we're going to learn this S is the Laplace transform. Right? So I can write H of S as R over SL plus 1 over SC plus R. Right? Right? And then I can like simplify. Right? I can simplify. So if I do that, I get R S squared LC plus 1 plus SRC divided by SC. So this is SRC divided by S squared plus SRC plus 1. Remember, S is I omega. Right? And if I plot this, this is my ideal band pass filter. This actually looks like this is this feature. Right? And obviously I have two cutoff frequencies. Right? So to find omega C1 and omega C2, I'm gonna have to solve absolute value of h of omega equals 1 over square root of 2. Right? And since this is a second order circuit, if I look at the absolute value of h of omega, it has like two roots. Right? Yes. What's your question?
You said earlier you had H of S, but
Yes.
like, wouldn't it still be H of omega?
No, I define S to be I omega.
Yeah, but then you're just doing H of I omega. That makes sense.
It is h of I omega.
I guess that makes
But
sense.
we're not writing I omega.
Yeah,
I was
but-
writing.
Okay.
And we can do the same thing for the bandstop filter. For intuition. For the bandstop filter. Again, remember a bandstop filter. If I have my x of omega goes to my system, which I know the ideal bandstop should look like this. Omega C1 and then omega C2. So y of omega is exactly x of omega if omega is greater than omega C2 or omega less than omega C1. And it is 0 if omega is between omega C1 and omega C2. Right? So if I build this circuit, again, I have two omegas, two cutoff frequencies. I cannot build it with the first order circuit. I have to build it with the second order circuit. So I have the input R, C, and L. If I look at voltage across these two, it turns out it is actually doing this. So if I take this to the frequency domain, I get the n of omega, R remains the same, C becomes 1 over I omega C, L becomes I omega L. And what I'm interested in is V out. What is V out of omega? Again, it's a voltage divider, right? I can combine these two because we treat all these elements as a resistor. So the numerator would be I omega L plus 1 over I omega C divided by R plus 1 over I omega L plus 1, sorry, I omega C plus I omega L. Right? Times Vn of omega. Therefore, H of omega is the output omega divided by the input omega, which is I omega L plus 1 over I omega C divided by R plus 1 over I omega C plus I omega L. Right? Again, let's just use the convention that S equals I omega. I can write H of S as SL plus 1 over SC divided by R plus 1 over SC plus SL. You can simplify it, right? And if you draw the magnitude of it, if this is omega C1, this is omega C2, I know the ideal filter would look like this. But this is the smooth out version of it. So it would look like this. Right? And we call this omega naught. How do we find omega C1 and omega C2? Well, it's the same as before. Omega C1 and omega C2 are the roots of the magnitude of h of omega equal 1 over square root of 2. Right? How do I find this omega naught though? Look what's happening at this omega naught. Magnitude of h of omega is 0. So to find this omega naught, I have to solve for magnitude of h of omega equals. Right? So that's what it is. Let me quickly remind you of something. Reminder. Low pass filter and high pass filter are first order filters because we can build them using first order circuits. Band pass filter and band stop filters are second order filters. Right? Why is it a second order filter? Because we need to build, we're able to build them using a second order circuit. Right? So let's quickly do an example. Quickly do an example. Let's just say I am given this circuit. This is R1. Let me redraw it. Then draw it. So let's just say I have this. I have this R1. And then I have this R2. And then I have this inductor with value L. And this is my input. And this is my output. Right? The question is, what type of filter is this circuit? Also, what is the order of this? Right? What is the order of this filter? That's the first order, right? I only have one storage element, therefore it is a first order. Right? If it's a first order, what are my choices? It's either like a high pass filter or a low pass filter. So let's figure out like which one it is. How do we figure out like what it is? We're going to have to look at the transfer function or the frequency response. So to be able to do that, we're going to redraw the circuit and frequency. Well, the input goes to frequency domain. R1 remains the same. R2 remains the same. What happens to the inductor? It becomes I omega L. And voltage across these two is VR. Right? What's the relationship between these two? They're in parallel. So I have R2 in parallel with I omega n. Right? What is V out then? V out is voltage across these two. How do I compute it? It's a voltage divider. So I know V out is R2 in parallel with I omega L divided by R1 plus R2 in parallel with I omega L times Vn of. Right? So what is my frequency response? Basically this portion of it. Right? So I have V out of omega divided by V in of omega, which is H of omega. Let's just write it. R2 in parallel with I omega L divided by R1 plus R2 in parallel with I. Right? Again, let's not write I omega. Let's just use S instead. So define S to be I omega. What is H of S then? It's R2 in parallel with SL divided by R1 plus R2 in parallel with SL. Right? So I can compute this. I have R2 times SL divided by R2 plus SL divided by R1 plus R2 times SL divided by R2 plus SL. Right? Let's simplify it a little bit. I have S R2L divided by R2 plus SL. I'm going to find a common denominator here, which is R2 plus SL. This one becomes R1, R2 plus S R1L plus S R2. Right? This and this cancel. H of S becomes S R2L divided by, I'm going to factor out this S. So it's R1L plus R2L plus R1. Right? Do you agree with that? Yeah? Remember, this S is I omega. So to know exactly like what it is, I have to look at this H of S, but look at the magnitude of it. So I'm going to replace it by I omega. So I have H of omega equals I omega R2L, I omega times R1L plus R2L plus R1, R2. What is the magnitude of it? It's the magnitude of the numerator divided by the magnitude of the denominator. Right? So it is omega R2L. Again, this is a complex number, right? If I have A plus IB, magnitude of this is the square root of real part, the squared, plus imaginary part squared. So I have square root of R1 squared R2 squared plus R1L plus R2L, the whole thing. Right? Right? What happens? I have omega H of omega equals omega R2L divided by square root of R1 squared R2 squared plus R1L plus R2L squared omega squared. Right? What happens if omega is 0? Well, since the numerator is 0, this is non-zero, absolute value is 0. What happens if omega approaches infinity? Well, numerator is still something like omega R2L. How about the denominator? Well, this term dominates the whole thing, right? Because omega is pretty big. So the denominator becomes R1L plus R2L times omega. Right? Yes or no? Yes or no? Well, this and this cancel. So this is basically R2L, R1L plus R2L. Right? Which is non-zero. So what is the filter that I have? What is the filter that I have? For low frequencies, I have something around 0. For high frequencies, that is some number. So it's a high pass filter. So it is a high pass filter. Right? Yes or no? Does that make sense? So that's it. Since it's a high pass filter, we know it is a first order as well. We already knew though, right? Because the circuit we started with was a first order circuit. So we're torn between high pass and low pass. But we verified it was a high pass. Right? So to determine like what type of filter you have, all you have to do is to basically find a frequency response, look at the magnitude of it, and see what definition this magnitude fits in. Right? You're rejecting low frequencies or rejecting high frequencies. You're rejecting a range of frequencies or you're keeping a range of frequencies. And given that, you can determine what type of filter you have. Okay? Does that make sense? Yes? All right, I'll see you guys next week. Yes, what was your question? Okay.